let's change the world a little bit today. There's something that's been bothering me, something that I've done some videos on, and I figured it out. We're gonna change the world just a little bit. The performance of AMD CPUs in some scenarios is way less than it should be. It's a bug in Windows, probably the Windows kernel, and I can prove it. Now, I'm not just talking about the Threadripper 2990 performance. I did another video on that. Nope. Also, EPYC CPUs, EPYC performance scenarios. Well, EPYC performance in some scenarios regresses just like Threadripper, and it's not AMD's fault. The system behind me, that is an EPYC 7551. It's about a $5,000 configuration. But first, let me catch you up to where we are now. How memory bandwidth is killing AMD's 32-core Threadripper performance. That's the headline. I'm not picking on PC World. They do pretty good work. But many others have also said this. I'm not picking on PC World at all. You know, smart people looked at this, and also me included, because I'm not one of those. And they look at 32 cores, and they look at 64 threads, and they look, it's only 4 memory channels. And they think, well, maybe that's why. Maybe that's why we observe certain programs like Indigo regressing with a 2990. 2990 ends up being slower than a 2950. Too many cores over not enough memory paths. There's contention, and certainly in some cases that might be true, but not this. Not what I'm talking about, and not with this severe of a performance regression. These weird performance regressions in apps like the Indigo renderer. We've seen it in Premiere Pro with certain plugins, 7-zip, some of the spec programs, and many others. And the conclusion is, oh, well, you know, it's memory because we're running at 4 channels instead of 8 memory channels. And you know, yes, I will concede sometimes that's true, but not here, and not with regressions this severe. Here we are, months later, and those specific regressions remain. Linux doesn't really suffer from these regressions, and yet many in the media are looking to AMD for answers. Still more have accepted that, well, it's just the way it is. 4 memory channels, it's not physically there, it's a physical difference, but not I. So you understand, for these apps, the Threadripper 2950, which is a 16-core beast, is the same speed or faster than the 32-core monster, the 2990 WX. And it did seem plausible that it could be memory, but that just didn't feel right to me. I mean, you look at it, you look at the performance, and you use the system, it doesn't make sense. It also doesn't make sense on the Linux side of things, because where there's Linux overlap, it doesn't really suffer the same way. Now, the other video that I did also talked about the Indigo rendering program and how if you fiddle with the affinity or disable core 0, the performance would improve dramatically. It's 50% faster. Now, Ian Cutress from Anantech, you know, is one of a dying breed of truly great journalists who can research and reason critically. He even put his master level skills to use to try to help me investigate what was going on with this. He ran some tests, he ran some of his benchmarks, published an article, which you should also definitely read for background to try to understand what's going on. Now, mostly his changes, disabling core 0, didn't really affect things positively. I mean, it did a little bit, and he could kind of see that because he could repeat what I did and the performance improved, but then in automation, the actual numbers didn't really match up with the numbers that I had. So definitely check that out. There's a link below. His results really left me scratching my head even more. It was like a telltale heart beating beneath my floor, gnawing at me, eating at me. And it's like this little mystery, this little thing in the back of my head that's like, I gotta figure this out. Because you see, Indigo on Linux runs like greased lightning on the Threadripper 2990. If it runs like greased lightning on Linux, that's not a hardware difference, that's a software difference. And also the performance with apps like Veracrypt and 7-zip generally are much better on Linux than on Windows on the 2990. So I tested some results of Linux on Windows, like looking at the Windows subsystem for Linux. And that left me with even more questions, but more on that in a sec. The whole process here led me to that. The EPYC server, literally EPYC, an EPYC CPU, a 7551. Let me go to the whiteboard and explain. Now, the Threadripper and the EPYC 7551 actually share a lot in common. There's really quite a bit here. If you look at the actual CPU, we've got 4 dies, 32 cores, 64 threads, both TR4, they both got guts. The TR the Threadripper 2990 has a higher clock speed. So this is clocked much higher than the EPYC. But the EPYC has up to 8 memory channels. That's what these are. So we've got 2 channels of memory with up to 4 DIMMs on the connection here. So really just 2 of these are populated. The motherboard that I have has 8 slots, so there's 1 DIMM per channel. So every core in the 7551, or every die, is connected to 2 channels of memory. So it works. But on Threadripper, on the 2990, in order for these cores to get at memory, they've got to go through the IF, the Infinity Fabric, in order to get at what's on memory, depending on where the memory it is that it's accessing. And so it's a little bit more latency, but honestly, it's not a lot more latency. And if Indigo is regressing because of memory bandwidth, as many have stated, well, let's take that out of the equation. Let's use the EPYC 7551 and run Indigo with its 8 channels of memory. So let's run that and see what that is. Check it out. The performance is still crap on the 7551, but it's got 8 channels of memory. We've got it configured with all 8 channels. The Indigo performance is basically identical to the 2990, even a little bit slower, but when you take into account the clock speed difference, it's basically identical. So Indigo is not limited by memory bandwidth because it's got half the memory bandwidth on Threadripper, and the performance clock for clock is basically identical. Let me be clear. Indigo is just a tool that we're using to explain a regression for certain programs. Now we must assume that it's not the software, it may be the hardware, or possibly the operating system, because other software other than Indigo does it. And we'll talk more about the software side of things. Now, in no uncertain terms, AMD is leading the way here. It's leading edge. It's innovation and creativity with hardware again. And this performance regression is not their fault. Look, AMD has led the way with gigahertz clock speed and integrated memory controllers and gigaflop stream processors, and now chiplets. That's AMD. All of those things, AMD was first. They innovated, they're creative, they're bold. They have to be, because I mean, that's what you do. And AMD always gets a black eye for taking those chances, but they're leading here. They're actually leading. These performance quirks are not an AMD problem, and they're not even really from trying to cram too many cores into not enough memory channels. The performance of the Threadripper 2990 and EPYC server CPUs has been gimped unnecessarily in some scenarios by some bug in the Windows kernel, and I'm proving it. But we got to go deeper. We're going to run Indigo with my performance tweak, the manual one, and capture information about what processes are running and on what cores. And then we're going to go run Indigo without my performance tweak and compare the data. The problem is that it's pretty clear it's not just the CPU affinity, it's also something else. But we're also going to run it in Linux under Windows, using the Windows subsystem for Linux. Now remember the video that I did on memcopy routine in the standard C library? Maybe we're looking at something like that here, where certainly it's been the case that an oddball memory copy routine in the system library will cause strange performance in random applications that depend on the system library. So maybe there's something in some library that's a part of the operating system that causes problems with some programs and not others. As a thought. I've fixed problems like that by updating DLLs or updating libraries that had been mistakenly bundled by vendors. Could be something like that. A lot of testing later. Unfortunately, no. But fortunately, Indigo is cross-platform. And so when we run it under Linux, there's no problem. But not when we run it under Linux under Windows. So here's our result on Linux natively. That's a score of over 3. It's almost double what we get on Windows. And that suggests that there's something going on here. It's the same hardware, it's configured the same way, but Indigo under Windows. So fortunately, you can run Windows apps under Linux. So let's deploy the Windows subsystem for Linux. So now we're running Indigo for Linux under Windows, which is kind of a neat trick. So absent the Linux kernel, really what's handling the process Indigo is the Windows kernel. And it handles running junk via the POSIX extension. So in layman's speak, we're running Indigo, but Indigo doesn't know much about what we're running it on. And Windows handles the process and the threads, the Windows kernel. And so Here's the output of ls topo. This shows us the topology of the machine so we can get an idea for cores and packages and layout and all this kind of stuff. It's all related. And it's all up to the Windows kernel to decide what it reports to Linux processes. But we can see here from the output of ls topo that it's just one package with 32 threads and we're basically done. But we know that Windows knows that there's 4 nodes here. So Linux can't make any decisions about how to handle the threads or how to manage the thing here, because Windows is not showing Linux anything about how the processor is arranged, which cores are close to memory or NUMA, none of that technical stuff. It's not sophisticated enough to do that. And look at that, the performance is crap. Even though I'm running Indigo for Linux, which works great under a real Linux machine, under a real Linux kernel, but it performs just the same crap on the WSL as it does on Windows. And yet here the CPUs really are running at 100%. They're busy doing something. You would think that you would have less CPU utilization if it's not as efficient, but the CPUs are actually pegged. So this strongly suggests that something is broken in Windows about dealing with these threads. Now if we look in Task Manager, there it is, there's Indigo for Linux. And it's confirmation that all the cores really are at 100%. And yet the performance counters are not showing that these threads are waiting on memory or IO or anything like that. It would seem that 100% of the CPU workload here is all going to whatever the process wants to do. That CPU utilization at 100% is true, whether the Indigo performance is crap or good. But clearly, the system is doing different stuff in one scenario or the other, even though the systems are, both running at 100%. So I reached out to Jeremy from Bitsum, and we took a look at what was happening with these threads by dumping lots of system variables from Windows. Now, I'm not really a Windows guy. I've got some Windows development experience, unfortunately, but there's a lot of little details here, and there's a lot of little details that I'm leaving out about the work that we did. We looked at a lot of things like the processor groups and BCD edit, and how Windows supports more than 64 threads, but it's got to be split into processor groups, which doesn't necessarily translate into like a socket. Yes, we did all of that. None of that was really useful. Well, I mean, we got information out of it, but you would think that setting stuff from the CLI as the process was being created would work, but no. When you use the start utility and you specify the affinity, it didn't really seem to help too much. And Ian Cutress' stuff shows that too, because he can run his benchmarks and create the process, but what I was actually doing was changing it after the process was already running. And when there was no performance regression? When I set the affinity manually via Task Manager, but also in UMA mode, Uniform Memory Access, which you can only do on the EPYC. On the EPYC 7551 with all of its memory channels populated. Now, UMA mode can be bad for enterprise users, so listen up, VMware people, because this might be relevant to your interests. There are server scenarios and server apps that behave like the game Grand Theft Auto. It's one of the ones that we looked at where it's like we can run it in Uniform Memory Access mode, but in doing so, it will hurt the GTA performance a little bit. They work better in NUMA mode versus UMA mode. And Process Lasso and Ryzen Master's dynamic local mode solve some of that. But that performance regression in GTA is not 50% worse between the two modes. I mean, between UMA and NUMA, it's not a 50% regression. And the 50% regression is what we're talking about here with Indigo and some other programs. The operating system, or possibly the app, needs knowledge of the hardware in order to be able to do the best thing possible. And with UMA, you can't do that. So in the case of Grand Theft Auto needs to be located in memory near the processor that is actually doing the work. Side note, this would be more complicated with a 2-socket system, because the latencies between 2 sockets and the memory attached to those 2 sockets is relatively astronomical. So our focus here is about one bug, single socket system. So let's not talk about that. Also, related side note, UMA is not possible on the Threadripper 2990. Remember the marker board? Some cores have direct access to memory and some don't. It literally physically cannot be UMA. So back to EPYC. To be clear, we ran the EPYC 7551 in UMA mode, meaning that all 8 memory channels were populated, and we changed the memory interleaving mode to die. And then Indigo performed great. No fiddling, nothing we had to do. As far as Windows knows, it's just one big happy pool of cores and threads. Indigo runs great in UMA with no hackery, as did 7-zip and a whole bunch more applications. Now, benchmarks from us on that soon, you know, UMA mode on the 7551, if Dr. Cutress doesn't beat me to it, because he's just fired up his benchmarking behemoth with his fancy new EPYC 7601. But, well, anyway, I digress. Back to the Threadripper 2990WX and the EPYC 7551 in NUMA mode. Why does fiddling with the affinity via Task Manager fix the performance of Indigo only after it's already running? Why does changing the affinity at process creation not seem to fix it? In terms of setting it to run on all cores or setting it to run on all cores but one, as Dr. Cutress tested. Now, Jeremy and I decided to dump as much info as we could about every scenario, and that's linked in the description on the Level 1 website. And so after a lot of digging and head scratching, because this is very, very WTF, we figured out that Windows suggests ideal cores to the scheduler that in fact are not ideal. And the CPU utilization remains 100% because it's spending all of its time shuffling threads around instead of actually doing the work in the threads. In fact, half the time is spent between shuffling threads and actually running the program, running the thread, in other words. Which is why the performance regressions are often as bad as they are. Now enter comaprison. It's a handy little utility that Jeremy has been cooking up. And we've added a checkbox to this thing that specifically fixes this crazy situation, threads that have been marked in this way by the Windows system. It's literally the NUMA disassociator. We're gonna get disassociated. That sounds painful. It's not really strictly correct to call it an affinity thing either. So when Indigo is going fast, the threads are set to a full ideal CPU range of 0 to 63. In either NUMA or UMA accelerated mode, it's the same either way. Full 4 of 4 NUMA nodes, always used. Ideal CPU, this ideal CPU could be anything in the set of 0 to 63 threads. But when things are going slow, the threads are set to a limited ideal range of just one NUMA node, which is only 16 threads out of our 64 possible threads. And it could be any NUMA node, but it's always just one, and we can see that. But the affinity mask for the CPU is still all CPUs. And since we don't actually see CPU utilization being lowered, this is a strong indicator that there is a bug here somewhere. Very strangely, Windows seems to be able to deal with the first NUMA overflow. So maybe there was a bug fix where it's like, when an application is doing this and the ideal CPU is not the one that's available, it'll overflow one time. And so we have 32 threads that are working correctly, but the other 32 threads are not working correctly. So when there's more than one overflow and whatever that desired hint thing is that's going on in Windows, it fails. And probably nobody noticed it because there weren't multiple there weren't multiple nodes on a single package, more than 2 anyway, before now, I think. So the conclusion of that is it's probably something in the Windows kernel. There's some upper part of this thread management process in the Windows kernel that assigns those default ideal processor hints that are used by some lower part of the scheduler, and that's where the disconnect is within the Windows kernel. We know this must happen after process creation and is not related to affinity because changing the affinity at process creation does not have an effect. So in comaprison, Jeremy has added this fix unknown problem checkbox to comaprison, which will look for threads that have been gimped in this way that we've observed and try to reset them, to reset those hints. So it doesn't change the affinity or anything like that, it just resets the hints. And I can confirm that this fixes Indigo. And if you may want to help test this, you have a multi-core system or a many core system, run this, let us know the results. I mean, that would be awesome. Level 1 forums, that'd be great. It works, the way that comaprison works with this little workaround is it checks through all the processes every so often so that the processes that are exhibiting the issue are reset. But there could be a problem if you have a process that's created and destroyed really quickly. It might not be observed. So we've still got some work to do and some benchmarks to run and some other stuff like that. So stay tuned for more on this from us. But if you do have the 2990 or the 2970, it should definitely help us test this. Now, I couldn't have solved this puzzle on my own. I mean, this is a basically a 100% performance increase in Windows for things like Indigo. So I want to reach out and I want to thank Jeremy from Bitsum. The AMD user community really owes him some thanks for the work that he's doing on Core Prio, Process Lasso, and more. So if you haven't checked out Process Lasso, you definitely should. I also want to thank Gigabyte specifically for supporting my mad science by providing a 2990WX retail CPU and some of the gear that I've used for testing here. Now the 2990WX system that's promised to Linus Torvalds, I haven't heard from him, but I'm sure I'll get up with him at some point. And if not, well, I'm sure Eric Raymond will like the system nonetheless. So Gigabyte also provided the EPYC motherboard that I used to testing, and you should definitely check out our build videos on the really high-end Gigabyte 2990WX system, as well as the EPYC server build. They're honestly, they're pretty glorious. They're pretty amazing systems. They're really, really good. This whole thing has been an adventure. It's been an adventure and a half. This was bugging me so bad. I did splurge to buy the EPYC 7551 because I wasn't really sure how long I would need it, and I might need it for quite a while in order to run this experiment. And I couldn't have done that without support from viewers like you and viewers, supporters on the Level 1 Patreon. I mean, so big thanks to you, our viewers, and our supporters on Patreon. Really, thank you so much for letting me have this adventure. It's exciting. I mean, I figured it out. I figured out what the performance issue was. I didn't just, run the benchmark and be like, that number's lower than it should be. Moving right along. Oh, and yes, this has big implications for Zen 2. In my opinion, it turns out that AMD knew exactly what they were doing with the 32-core Threadripper. The memory bandwidth problem now appears to be far, far overstated. And if we're talking about the possibility of 8-core chiplets, still with 2 channels of memory and, 64-core, 128-thread single-socket systems, I'm not really sure that's been confirmed for Zen 2. But if we are talking about that, I am much less worried about memory bandwidth now, because we've basically got the EPYC 7551 and the 2990WX at parity clock for clock, which means the 2990WX is a little bit faster. I'm Wendell. This is Level 1, and you can find out more information at the Level 1 website. Join the Level 1 forum if you want to help us fart around, because I couldn't do these projects without support from the community. So there's probably follow-up information and all kinds of other stuff like that in the forum. So I'm Wendell, I'm signing out, and I'll see you there.